Hi students, hope everyone is fine and safe. It gives me immense pleasure to welcome you all to my new video, and today's video is about another interesting topic in unit 3. We're going to see floating point number representation. In this video we're going to see how to represent floating point numbers, what is meant by normalization, what are the different types of normalization, and what is the importance of biasing in floating point numbers. That is what we're going to see. This is the very basics for floating point representation. So first we'll start with what is floating point numbers, right? So before seeing floating point representation, we normally know that numbers, different numbers, right, in number system, right? And very basically, you would have come across integers and fractions, correct? And fractions, right? So what is integers? You know that integers is nothing but a full value which does not have a decimal point, right? Like this, 72, 26, 32, something like that, right? That is called as integers. And there is something called fractions as well, right? In fractions, it's like 0.5, 0.25, right? All those are called as fractions, right? You know about fractions as well, correct? And there is another particular numbers which is called floating point numbers. That is because here, if you take the 72, it is fixed, right? Even in fractions 0.5 or 0.25, right? This decimal point is fixed. Okay, so we can call it as fixed point representation as well. Okay, and what is floating point numbers? For example, right? If we take this number, okay, if the decimal point of this number, right, if the decimal point of this number can able to move right or left, then that is called as floating point number. That is, we can represent this particular number, consider this as a decimal number, right? And if you're going to represent this particular number using floating point, right, what we can do is we can do it like this, right? 1.06, or we can also represent like 0.106, right, into 10 to the power of 1, and here into 10 to the power of 2, something like that, right? That is, we can able to move this decimal point here, or something like that, right? So that is called as floating point numbers. Okay, so floating point is nothing but the decimal point or the radix point. We can able to move that radix point, right, in any particular number. That is why it is called as floating point numbers. Okay, and this is very basics about numbers, right? Why is that we want to study about floating point numbers here, right? We already know computers use binary values, zeros and ones, to represent any numbers, right? It saves values in memory, right? It executes all the instructions. Everything is based upon the binary representation in computers, correct? Right? So, for example, if you want to represent a scientific number, right? For example, like Planck's constant or Avogadro's number, right? In computers, okay? Then definitely you need floating point representation, right? And that is why we're going to see this particular topic as a very important topic. Okay, so any particular values, any particular scientific values which is stored in the computers will follow this floating point representation, right? And before moving to floating point representation, we will see what is fixed point representation, right? As I said, if you say this is a fixed point number, right, we know that before the decimal point, right, all those are called as integers, correct? All this called as integers, and after the decimal point is called as fractions. Right, after this decimal point is called as fractions. Okay, and this is a fixed point representation, which means each and every bit has its own bit positions, right? That is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. Similarly, 2 to the power of -1 this side, -2, -3, like that, right? That is, after the decimal, we will represent in terms of minus. The power will be in terms of minus, correct? Right. So if you take this particular number alone, the smallest number will be this one, right? Everything will be 0 except this one, right? That will be the very smallest number you can represent it with this particular number, correct? And similarly, the largest number is, if everything is 1, so it is this number 31.875. Okay, So in fixed point representation, the decimal point will be fixed. Okay. So before the decimal point, it is called as integers, and after the decimal point, it is called as fractions. Right. And you have to know range and as well as precision. Right. Range is nothing but a difference between the largest and the smallest number. A range, a specific range, 0 to 10. Right. 0 to 20. For example, if you take decimal point representation, its range is 10. Right. From 0 to 9. So it is, the total number is 10. Right. You represent from 0 to 9. Correct. Right. That is called as range. Right. And what is precision? The smallest possible difference between two numbers. Right. That is called as precision. Right. More importantly, right, in precision, like for example, if you take this decimal point, okay, take this is a decimal point, right. If there is more numbers in the left hand side, that is in the integer part, then that is represents about that will speak about the range. Okay. And if the smallest difference, that is the difference between two numbers is very small, and that is called as precision. It will be represented at the after the decimal point, right? That is, it has more bits in the fractional point part, okay? Whereas the range, it has more bits in the integer part, okay? So this is known as fixed point representation, right? Now we'll go to floating point representation, okay? So I'll take one particular example here, okay? Right. So I've already said what is floating point, correct? So floating point is nothing but the decimal point will move, correct? For example, you take this particular representation, 5.625, right? The corresponding binary value for this, right? You know how to convert this decimal to binary, right? So this you have to do it by division method, and this is by multiplication method, correct? And so you'll get this particular binary value, right? So if you have any doubts in binary to decimal conversion, we have already posted a video for decimal to binary and as well as binary to decimal. You can go through that, okay? So the corresponding value for this 5.625, the binary value is 101.101, correct? Okay. Now, as I said in floating point, right, at this particular decimal point can able to move the decimal point, right? So, for example, if I'm moving this decimal point here, that is 1 point here. So, what I can write is, I can write 0.5625, correct? 5625 into 10 to the power 1, right? I have to move it here, right? And similarly, if I move this point here, right? What I can do, if I move the decimal point here, it will go to 10 to the power of 2, right? If I move it here, it will be 10 to the power of 3, right? That is what represented here, right? You can see here 5.625. It can be represented as 0.5625 to the power of 1, right? And you can see this decimal point is moved here, so it is 2 to the power of 3, right? So what do you understand from this, right? That is, this value is represented as 0.5625 into 10 to the power of 1, correct? That is, this part, this number has 3 representation. That is, first thing is, it does not have any minus sign, right? And we know that if there is no minus sign, right, it is a positive number, okay? So it is a positive number. So it represents it has a sign bit, right? That is, it has a sign, right? And this number, you can see here, you have a decimal point, and after the decimal point, you have some numbers, right? And here you can see an exponent number, that is 10 to the power of 1. That is, we have moved the decimal point here. So we have represented as 10 to the power of 1. Okay. So to represent a floating point number, right, we have to go for floating point representation. Okay. Sir, what is floating point representation? Now, as I said, this number, right, is represented using floating point representation, right? That is, you have signed bit, you need exponent bit, and you need mantissa. Right. So what is signed bit? Signed bit will be either 0 or 1. Right. So if it is 0, then it is positive. So here it is positive number. Okay. And what is exponent here? Exponent is 10 to the power of 1. Right. As of now, you just understand what is exponent, what is sign, and what is mantissa. And what is mantissa? Mantissa is this fractional part. Okay. 5.625. Right. So this is the floating point representation. Okay, you have a sign bit, you have an exponent bit, and you have mantissa. Correct? Right. So far clear? Okay. Now I take the same example. Okay, 101.101, right? And I said that we can represent in floating point representation, we can move the decimal point, right, at our convenience, correct? But we have to represent correctly, right? So for example, now I move this decimal point here, 10.1101, right? If I represent like this, into 2 to the power of, I have moved just 1 point, correct? So it is 2 to the power of 1, correct? That is moving towards the MSB, correct? And if I move it here, right, that is 1.01101. If I move like this, I have moved decimal point 2 twice, that is 1 and 2, correct? Right. Similarly, if I move it here, 1.101, correct? So it is 2 to the power of 3, right? Similarly, we can move it the other side as well, right? If I move like this, right, 1.01, I'll represent as 2 to the power of -1, right? If I remove the decimal point, that is, if I move the decimal point here, right, at the very end, that is 101, right? That is 2 to the power of -3, right? So this is the problem in floating point representation, okay? That is, you can represent any particular number at any convenience, right? Like, depending upon that particular value, right, the exponent values will change, that's all, okay? But there should be a standard form for this, right? And that is why we go for something called normalization. To standardize the floating point representation, we go for something called normalization, right? Normalization. Sir, what is normalization? Right, that is to standardize this particular representation, we go for normalization, okay? So in normalization, you have to understand there is two representation. One is explicit representation, another one is implicit representation. Implicit, I'll show the example, but for as if now you understand what is explicit and what is implicit representation, okay? That is moving the decimal point to the left of the MSB 1, okay? That is called as explicit, right? If you take any particular number, I take this number itself, that is 101.101, right? The MSB has to be always 1, okay, in any number, right? So you cannot consider 0 as an MSB according to normalization, okay? That is moving a decimal point to the left of the 1 MSB, right? That is called as explicit normalization. To the right of that 1 MSB, that is called as implicit representation, right? Now you can see I'm going to write this as an explicit representation. I'm going to move this decimal point to the left of this MSB, right? Here MSB is 1, okay? It is not MSB, it is like the MSB must be 1, right? Moving to the left of the MSB 1, right? That is the exact definition, okay? Right? So it is 0.101101. This is explicit representation. You can see here I'm moving the decimal point to the left of the MSB. This is the MSB. I'm moving to the left of the MSB, right? And now what is implicit representation? Implicit representation is I have to move this decimal point to the right of the MSB 1, okay? You can see here that is 1.01101. So this is explicit and this is implicit, right? You understand now what is explicit normalization, what is implicit normalization, right? Right? You can see here. So as I said, what is explicit normalization? Moving the fixed point to the LHS of the most significant one, right? That is most significant one, right? That's one is very, very important, not the MSB, right? It is the most significant one in the bit sequence. You can see here, right? This is moved towards here, that is 0 point, right? And what is implicit normalization? Implicit normalization is moving towards the right, right? That is right of the significant 1 MSB, right? That is 1 point, okay? And now you can understand that explicit normalization will always start with 0 point, right? And implicit normalization always starts with 1 point, correct? Right? That is, you can see here, it starts with 0 here and it starts with 1 here. Any number, because what we are going to do, we are going to place the MSB to the left of the must be 1, right? You're going to place the decimal point to the left of the M must be 1, correct? So any explicit normalization will start with 0 point, right? And similarly here, it starts with 1 point, right? So why is that I'm particularly saying this? Because we have a formula for explicit normalization and as well as implicit normalization. Okay, so what is the formula for it? Okay, so you can see here, I'll just explain that formula, right? That is nothing but, we know that in any particular representation, right? In any particular representation, I said, like, as I said, in any floating point representation, you'll have a significant bit, you'll have an exponent bit, and you have a mantissa, correct? Right? So you can see here, this is the formula, -1, yes, into 0.m, that is, after dot, we will place the mantissa, correct? And it starts with 0.m, correct? And into, right, you will have an exponent, correct? So exponent will be e to the power of e minus bias. I'll tell you what is this bias. Okay, so this is explicit normalization formula. And if you see implicit normalization, it is -1, the same formula, -1 the power of s into 1.m, right, into 2 the power of e minus bias, correct? Okay, so it starts with 1 dot and here it starts with 0 dot, right? And you know, you don't want to worry about the signed bit. Signed bit will be either 0 or 1. And why is that I have represented -1? Because if it is 0 here, that is signed bit will be either 0 or 1. If it is 0, anything to the power of 0 will be 1, right? And if it is 1, right, what will happen? It will be -1, right? So it will be either positive or negative, right? Right? So that is why the formula is written like this. Now you understand what is explicit normalization, what is implicit normalization, correct? Right. Now we go to a very interesting topic which is called as biasing, right? You can see here in this particular formula, there is something called bias, correct? Right? So why is that we need bias, right? In any particular binary representation, if you take any binary representation, 8421 code or any number of representation, right, representing a minus sign, right, you don't have a specific range to represent a minus sign. Okay, here, like as I said, in floating point representation, you can see here there will be numbers with an exponent of -1, -2, -3, -8, like that, right? So how can we represent those minus exponent values, right? In order to represent those minus values, there is no particular representation in binary, right? That is any specific range. You cannot mention a specific range in binary numbers. For example, if you take 8421 code, right, it will be only positive numbers. If you take 2's complement representation also, there will not be a specific range, starts from minus value to plus value, right? So what we are going to do is we are going to deal with the concept called biasing. Okay, so what is biasing, right? So biasing is nothing but, like, for example, right, consider a 10-bit number. I'll just tell an example here. 10-bit number. If you take this number as 10 bits, right? Then 5 bits will be mantissa, right? 1 bit will be sign bit. We know that it will be 0 or 1, and 4 bit will be for representing the exponent. Okay, so 5 plus 4 9, 9 plus 1 10. Okay, right? So now if I take the 10-bit representation, okay. So if it has 10-bit representation, what I can do is 10-bit, it's a 4-bit here, right? So 4-bit in the sense 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. This is the 4-bit, right? The maximum value will be 8, correct? Maximum value will be 8, okay? So now what I will do is, right, for 8, that is, even if you take 8421 code, right, it will start with 000 and will end with 111, correct? Alright, so total numbers will be 16 numbers, correct? There will be a 16 representation, correct? So in order to represent a minus values, what I will do is I'll take a specific range here, right? That is, I'll take from -8, that is, I am taking only 4-bit representation. So what I'm doing is I'm taking minus 8 till 7. You can see here minus 8, minus 7, minus 6, minus 5, 4, minus 3, minus 2, minus 1 till 7. Okay. And now what I'm going to do is I'm going to add a bias value. Bias value in the sense plus 8. We are taking a 4-bit number. So what I'm doing is I'm doing a plus 8. If I add plus 8 to all these numbers, what will happen? You can see here, the range will start, it will be range from 0 to 15. You can see here, right? 0 to 15, correct? Right. If you add all these things, it will be a 16 numbers, right? Same like 8421 code, right? Now, what is the advantage of this particular representation? By using biasing, I can range the negative values as well, right? I can range negative values as well. Okay. Now, if you don't understand this concept, right, don't worry. Right. Well, next explanation, you can understand what is biasing. Okay. Right. So far you understand, right? Why is that we go for biasing? In order to specify the range for negative numbers to express the exponent values. Okay. Right. And now listen very carefully. Now, you know that in order to represent a particular floating point number, floating point representation, you need sign bit, exponent bit, and as well as mantissa. As I said, consider only 10 bits as if now. Okay, 10 bits as if now. Okay, now I take this example. Now what happens? 0.0101, correct? 0.0101, right? Now what happens? 0.101. I just shift this decimal point towards the right here. You can see here it is moved here. It is moved here, right? So it is moved here. So it's 0.101. Correct? That is what we are doing here. We are doing an explicit representation. Correct? That is moving the decimal point to the left of the 1. Right? M must be 1. Correct? Right? So into 2 to the power of minus 1. Correct? Right? So now now this number, how will I represent using floating point representation? You know it is a positive number, right? So sign bit will be 0, right? And exponent here, you can see here it is 2 to the power of minus 1, right? So you know that biasing 2 to the power of minus 1. See here 2 to the power of minus 1, right? For minus 1, what is the value? Positive 7, correct? For minus 1, it is positive 7, correct? So positive 7, how will you represent? How will you represent in 8421 code, right? Because it is 4 bits, right? It is 4 bits, as I said, right? So if it is 4 bits, how will I represent in 7, 0, 111, correct? That is 7, correct? So 0, 111, correct? Right? And then what we have to write? Then we have to express mantissa, right? We have to represent mantissa. This is sign part, and this is exponent part, and then we have to represent the mantissa. Mantissa is 5 bit. This is 4 bit. This is 1 bit. Mantissa part is 101, right? And then you have 2 more bits, right? Then 0, 0, correct? And that is what represented here. You can see here 0, 0, 111, right? 101, 00, right? So this is called floating point representation. Okay, right? This is explicit representation. Okay. Now I'll do the same thing with implicit representation. What we can do is moving to the right of the decimal point. Here you can see here it is moved to the right of the decimal point here 1.0, right? So it is 2 to the power of 2, right? So if it is 2 to the power of 2, what I have to do? Go here 2 to the power of 2, right? So what is the value? 10, right? The biasing value is 10. If it is 10, what I have to do? Right? 8421 code. What is that? 0, right? That is 8421 on 8, right? 1, 0, correct? So here this point is represented as sign bit is 0, right? And exponent is 1010, 1010, and remaining point 01101. You can see here 01101, right? So that is mantissa, right? Now you understand what is implicit representation and what is explicit representation, right? See, this is very basic to understand IEEE floating point representation. Okay, right? So only if you understand this concept, you can able to understand single precision, double precision as well. Okay, right, sir? It is very difficult for me to calculate this bias value every time, right? So that how will I calculate very easily, right? For minus 1 it is 7, for 2 it is 10, right? All you have to do is you have to know what is the bias value, right? So here it is a 4 bit, right? So what I did is I consider 4 bit like it is the bias value is 8, right? So all you have to do is you have to add the bias value to this number, that is minus 1 plus 8. So it is 7, and that is why we are representing 7, 0, 111, right? Here it's 2, 2 plus 8, it's 10, right? And that is why it is represented as 10, right? So you can easily represent, you can easily remember this, right? So this is the importance of bias value to represent the exponent, okay? Right? Now we have seen what is explicit representation, what is implicit numbers representation, how it is helpful for floating point representation, right? And very importantly, right, in computers, normally right now what we use is, we use only implicit normalization, right? We use only implicit normalization, right? Why? Why is that implicit normalization is used, right? Right? So I'll tell you the same, right? We know the formula for it, right? We already know what is the formula, right? And as I said before, you can take the same example, 5.625, right? If the binary value is 101.2, right? This is explicit representation, and this is implicit representation, okay? Just I explained how we represented explicit and how we represent implicit, right? Same I am explaining here, okay? Right? So sign bit is 0, right? And here you can see here the decimal point is moved 3 times here, right? So it is moved 3 times here, so it is 2 to the power of 3, right? So if 2 to the power of 3, 3 plus 8 is 11, correct? 8 is 11, right? So the remaining part is mantissa, correct? 1 0 1 1 0, right? That is, you can represent only 5 bits, 1 2 3 4 5. You have to neglect this number, okay? And you can see here it is represented like this, 0, right? And what is the exponent? 1 0 1 1, right? And mantissa part, we are excluding the last part because only 5 bits can be represented in here, mantissa part, okay? So this is explicit representation, okay? And implicit representation, what you will do, what you have to just move it towards the right of the MSB, correct? Here what we have done, we have moved to the left of the MSB, here right of the 1 MSB, right? And so you can represent as 2 to the power of 2, right? So sign bit is 0, and 2 plus 8 is 10. So this is the exponent, you can see 0 1 0 1 0, and the remaining value is only 5 bits, so 0 1 1 0 1, correct? Right? Now we have already seen this, right? Explicit and implicit normalization. Now, sir, how is that we say implicit normalization is the best one when compared to explicit normalization? Okay, right? Why is that implicit normalization is only preferred? Right? That's because I'll just decode this. Now we go in reverse order. Okay. Now you understand that this particular number, right? This particular number in computer memory, it will be saved like this. It will be saved like this, okay? Right? If this number, it will be saved like this, right? That is the understanding you should have for this representation, okay? Right? Now, why is that implicit normalization is better? I just decode from this one. Say, for example, this is already stored in computer, right? So, how will we decode it, right? You can see here, this is already stored in computer. So, this is explicit normalization and this is implicit normalization, right? We already know this is the value, correct? Right? So now if we decode it, we have to get this particular value, correct? So this is the formula which I said, right? Minus 1 to the power of S, 0.1 M, 2 to the power of E minus bias, correct? Right? We know bias value is 8, correct? Bias value is 8, right? So now to this is the computer representation, okay? From 0, right? If you put 0, right, what will happen here? It is positive number, right? That is, it will be 1. So it is positive, right? So from 0, you understand that it is a positive value, right? And what is the exponent value here? You can see here, right? In 8421 code, if you decode it, what will happen? 8421 code, say 8, 10, 11. So the exponent value is 11, correct? Right? And this is the mantissa part, right? 10110, correct? Right? So it is the mantissa part. So mantissa part, right? How will you represent mantissa part? It's 1, 0, 1, 1, 0, right? And what is the bias value here? It's 8, right? We know that this is the formula, right? So the exponent value minus bias, that is the original bias, right? Because we know that in exponent, what we are doing is we are adding the bias value and representing the exponent, correct? Right? So we have to, in order to decode it, we have to remove this exponent value, that is bias value, right? So now we know that the exponent value is 11. 11 minus 8, what will happen? 11 minus 8 is 3, correct? It's 2 to the power of 3. Correct? Right? Now you understand if it is 2 to the power of 3, right? So what will happen here? Pro 3, this is the mantissa value, right? So it's 1, 2, 3, right? You have to represent like this. You have to represent like this. So 1, 0 dot, 1, 0, 1 dot, 1. Got it? Right? So now what will happen? Now what will happen? You just convert this to decimal value, right? What will happen is you'll get only 5.5. You'll get 5.5, right? But the original value is 5.625, right? Now coming back to this, okay, what will happen? Right? Here it is 0 point the mantissa value 10110, correct? And that into 2 to the power of 3, correct? Right? So similarly here, right, if you understand here, it is 10, right? It is 10. So if you represent using the implicit representation, what will happen? Minus 1 to the power of s, 1 dot m, that is 1.01101, that is the mantissa value, correct? Right? And exponent value is 10. So it is 2 to the power of 10 minus bias. 10 minus bias is nothing but what will happen? 10 minus bias, it's 2, right? So we have to move the decimal point 2 times, right? So so you have to move the decimal point here. So it's 101.11101, correct? Right. So this value is 5.625. You're getting the exact value. That's because you can see here this one, right? This one here it is 0, correct? 0, right? So if we just decode the same representation, we get the exact value in implicit normalization, but we get only 5.5 in explicit normalization. Okay, and that is why in computers normally we use only implicit normalization. Okay, right? So today what we have seen is we have seen what is floating point number, what is floating point representation, right? What is sign bit, what is exponent bit, what is mantissa, and what is normalization, what is meant by biasing, right? All these are very, very important because this is the very basic to understand single precision and as well as double precision. Okay, right? So now you have to be very clear. Any particular exponent value, you have to add it with bias, right? So you have to know for any representation what is the bias value, right? So that is very, very important in normalization, in floating point representation. Okay, I hope you understand the logic, right? Thank you, students.
Thank you, students. Thank you for watching. கண்டிப்பாக இந்த வீடியோ உங்களுக்கு எல்லாருக்கும் ரொம்ப யூஸ்ஃபுல்லாக இருக்கும்னு நம்புகிறேன். Subscribe Passionate Professor and keep learning. Thank you very much.